This entire unit, 5.2 on AC circuits, is really a study of one particular circuit. What's the behavior of a circuit that has an inductance, a resistance, and a capacitance? The LRC series circuit. Well, here's what we've come up with so far. The current in this circuit is sinusoidal and can be expressed as instantaneous current is max current times cosine omega t. The voltage across the resistor at any given instant is equal to R times instantaneous current, so it's IR cosine omega t. The voltage across the inductor at any instant is L di dt, so it's equal to negative omega L I sine omega t, which in turn is equal to negative X sub L, which stands for inductive reactance, times I sine omega t. The voltage across the capacitor is equal to Q over C, and charge is the integral of I dt. So we get the voltage at any instant is equal to I divided by omega c times sine omega t, but that's just as good as x subscript c, I sine omega t. So we have some values of resistance that we refer to as reactance. The inductive reactance is equal to omega L. The capacitive reactance is 1 over omega c, and of course the resistance of the resistor is just R. If we make a phasor diagram to represent the current along with all the voltages, actually let's leave the current out of it. There's actually not much of a need to include a phasor for the current, and here's why. If this phasor represents the voltage across the resistor, then we know the phasor for the current lies along that same line, because current and voltage across a resistor are always in phase with one another. However, voltage across an inductor always leads the current by 90 degrees, and the voltage across a capacitor always lags the current by 90 degrees. So in this phasor diagram, I'm consistent with the one from our last video lesson, where this must be a circuit where the frequency of the generator is slightly higher than the resonant frequency. So we say omega is greater than omega naught. Omega naught represents resonant frequency. The reason I know it's a greater frequency is because you can see the voltage across the inductor is a longer vector than the voltage across the capacitor, and the only way voltage across an inductor would be greater than voltage across a capacitor is if omega is large. There's a direct relationship. As omega goes up, voltage across an inductor goes up. As omega goes up, voltage across a capacitor goes down. So we can reduce this phasor diagram to look like this. Keep the voltage across the resistor unaffected, but we can replace the voltage across the inductor and the voltage across the capacitor with one single vector that represents the difference between the two. So there's VL minus VC. So if we want to find the total voltage for the circuit, we need to add using the Pythagorean theorem. We need to find the hypotenuse of this right triangle. So the EMF is equal to the square root of VR squared plus VL minus VC, quantity squared. And if we make some substitutions, we find that the EMF is just equal to I times Z, where Z represents not resistance, not reactance, but impedance. And impedance is equal to the square root of r squared plus omega L minus 1 over omega C quantity squared. Now this leads us to something known as phase angle. We know that the relationship between voltage across the inductor and voltage across the resistor, they're 90 degrees out of phase. Eli, the Iceman. Voltage across an inductor comes before the current. It leads the current. Voltage for a capacitor comes after the current. It lags the current. So the voltage across the inductor in a phasor diagram is 90 degrees ahead of the voltage across the resistor. Because after all, voltage across the resistor and current always point in the same direction. The ice part of Eli the Iceman. Voltage across the capacitor lags behind the current by 90 degrees. But how far out of phase is the EMF of the circuit with the current? Now let me draw the current phasor back in. We know it's in phase with the voltage across the resistor. So isn't this interesting? The EMF of the generator is not in phase with the current. It would be if it was driven at the resonant frequency, but at any frequency other than the resonant frequency, there's a phase relationship, a phase angle we'll call phi, between the EMF and the current. So let's see if we can figure out what that angle would be. Well, we just have a right triangle here. This side of the right triangle is the voltage across the resistor. This side, the hypotenuse, is the EMF, and this side is the difference between the voltage across the inductor and the voltage across the capacitor. And so this angle phi represents the phase angle. So, knowing what we know about right triangles, tangent of an angle is equal to opposite over adjacent. So the tangent of the phase angle should be equal to VL minus VC divided by VR. That's one way to say it. Or we can make a substitution. Tangent of the phase angle is equal to voltage, maximum voltage across an inductor is inductive reactance times current. Maximum voltage across a capacitor is capacitive reactance times maximum current. And maximum voltage across a resistor is resistance times the maximum current. So we can just divide out the max current in numerator and denominator, and then it's just as well to say tangent of the phase angle is equal to inductive reactance minus capacitive reactance divided by resistance. We can make yet one more substitution so that we have, got ahead of myself, 3 different expressions to be used to calculate phase angle in an LRC series circuit that's driven at some frequency other than the resonant frequency. Here's the third formula. Tangent phi is equal to omega L minus 1 over omega C all divided by R. All 3 of these are equivalent. It just depends on what information exactly you're given in some particular problem. In the next lessons, we'll try to give some numerical examples of how we can put all these formulas together that describe the behavior of the LRC series circuit.